Hello, and welcome to an introduction to the cross product. In this video, we will learn how to compute the cross product by the geometric approach and also get familiar with some typical usages of the operation. The cross product is a product operation between two vectors which results in another vector. For this reason, the cross product is also called the vector product. There are two approaches for computing cross product, geometric and algebraic. To perform the cross product by the geometric approach, we bring the two vectors into one initial point and measure the smallest angle between them. The cross product u cross v is a vector. Let's call it w. This vector has magnitude equal to the product of the magnitude of the vectors u and v times the sine of the angle between them. Vector w is orthogonal to both u and v and pointing to the direction determined by the right-hand rule. Here the cross product starts with vector u, so if we curve our right hand's four fingers from u to v, the right-hand rule says that our thumb points the direction of the cross product u cross v. In class, we'll learn how to compute the cross product algebraically, and unfortunately, the process is more complex than that of the dot product. Unlike dot product and every other operation you know, the cross product is not commutative. Examples are if you compute I cross j, where I and j are unit vectors in positive direction of the x and y axis, respectively. You have vector k, the unit vector in the positive direction of the z-axis. But if you switch the order of the product, the resulting vector is the opposite. Commutativity in a lot of mathematical operations, such as 1 plus 2 equal to 2 plus 1, is something most of us have been taking for granted for a long time, but it's actually not natural. In our daily lives, order matters with, for example, socks and shoes, or following a food recipe. The cross product comes with many applications. By its definition, we know that the cross product can be used to find a vector orthogonal to any two arbitrary vectors. Also, for two vectors that are parallel, the angle between them is either 0 or pi. In this case, the sine of this angle is 0. This implies that the cross product results in vector 0. And we can use this as a test for detecting, for example, if two lines are parallel. Another practical usage is finding area of a parallelogram or a triangle. If you are given a parallelogram, you can first find two vectors that generate the figure as shown, and the area is simply the magnitude of the cross product. Calculating the area of the triangle is done similarly, but we need to divide the magnitude of the cross product by 2. We have just learned briefly about the cross product, about how to compute it via the geometric approach. We have also learned a few typical usages of the operation. In the section that follow, we'll use this product along with the previous vector operations we have learned to perform more interesting computational tasks.